Let's talk about absolute convergence and the ratio test. So one of the conditions of the integral test that we had was that each of the terms an had to be positive. Another way of saying that is that we needed our an to be greater than, or let's say greater than or equal to 0. Okay. So what I want to do now is I want to consider a series that looks like this. Let's say that we have this infinite series as n goes from 1 to infinity, and we got an. So it's just a typical series that we're used to working with. But in actual fact, it looks like this. We can rewrite it as the summation as goes from n from either 1 or 0, depending on the problem. And we're going to put this negative 1 to the n in front, and then a bn like this. So this negative 1 to the n in front, this part is what we call the alternating piece. In other words, that's going to cause the sign of each term to alternate. So this causes the SIGN of each term to alternate. Okay, so it goes from plus to minus to plus to minus and so on. And if we look at this second term here, this BN piece right here, this part we're saying, you know what, we want our BN to always be greater than or equal to 0. So instead of every single term being positive, what we're saying is that it actually alternates in sign from positive to negative to positive to negative to positive to negative. So if you were to look at the signs of a series, it would be like plus, minus, plus, minus, plus, minus, something like that. And when we have a series that looks like this is an example of something called an alternating series. Okay, so we actually have an entire section dedicated to looking at alternating series. So what I want to do at the present moment is I want to talk about the difference between these two cases. One case where you sort of have a series that's always positive, and one case where you have a series that's alternating. And when you have a series that's alternating is more likely to converge than a series that does not have an alternating piece. By that, I mean looking at something like the summation as n goes from 1 to infinity of 1 over n versus something like the summation as n goes from 1 to infinity of negative 1 to the n times 1 over n. So what I'm trying to say is this series on the right is more likely to converge than this series on the left. And the reason why is because if all the terms are positive, you're worried about this exploding off to infinity. You keep adding numbers that make it bigger and bigger and bigger. But when you have the alternating piece, half the time you're subtracting a number, and the other half of the time you're adding a number. So I think that increases the chances of your series converging than a series that does not have this alternating piece. Okay. Another way of saying that is our series that looks like this, the summation as of an as n goes from 1 to infinity, this is more likely to converge than a series that looks like this with the absolute value of an in there. Because this series on the left over here, this one could be alternating, which increases the chances that it converges. Whereas if I took absolute value of the inside, that would remove the alternating piece, so your series might not converge. Okay, so this part here, may have an alternating piece. Okay, so now we're in a position to define what it means for a series to be absolutely convergent. Okay, so we have a series summation an is called absolutely convergent if this infinite series as n goes from 1 to infinity of the absolute value of an converges. In other words, if we slap absolute values on the inside and your series still converges, then we say it's absolutely convergent. And one of the tests that we're going to learn in this section is a very powerful test called the ratio test. So what does the ratio test tell us? Well, actually, it's powerful because it tells us about absolute convergence. So let me explain to you how this test works. What we're going to do is we're going to construct a ratio. We're going to take an plus 1 and divide that by an. We're going to take absolute value of this ratio, and then we're going to calculate the limit as n goes to infinity. And we're going to call whatever number this is, we're going to call this number L. Okay. Now, let me break this ratio down for you. This denominator here is the general term. This numerator is the term that's immediately after the general term. So this is the next term after the general term. We take the ratio. We want to take absolute value, so you don't worry about the sign. And then we're going to take a limit. And we're hoping that that limit is equal to a number. Okay. Now let's say that that limit was less than 1. If that limit was less than 1, then this means that your original series an is absolutely convergent. So I'm kind of lazy. I write this ABS CGS to mean absolutely convergent. Okay. If you took this same ratio, so remember, you're looking at the ratio of the subsequent term to the general term, and you're dividing those two guys and taking the absolute value and taking the limit as n goes to infinity. Again, that's still that same number L. You know what? If this ratio was bigger than 1, then this means our infinite series an diverges. Okay? So if we look, we look at the same number L here. If L is less than 1, that means it's absolutely convergent. If L is bigger than 1, then that means it's divergent. So the natural question that you're asking is, hey, what happens when the limit as n goes to infinity of this an plus 1 over an in absolute value equal to L? What if that's equal to 1? And in this situation, the test is inconclusive. That means, we need to try another test. Need to try something else. Okay, so I'm going to highlight this last case over here just because it's kind of a big deal. So this test is super powerful, ratio test. The only thing is, you know what? There's one situation where the test is inconclusive, and then we need to try something like either an alternating series test or an integral test or a comparison test or a limit comparison test or something like that. Okay. All right, everyone. We'll look at some examples in class. Take care.